Equilibria in chemical industry 8.5. Okay. The major portion of this part is something that you have studied back in IGCSE, going to relate it with the same principles and how dynamic equilibria are disturbed with the help of certain factors, concentration ho gaya, pressure, temperature, catalyst, that kind of stuff. But this time it's going to be a little bit better and advanced since you have studied more about the equilibria and factors interrupting them. Now, understanding of equilibria, chemical industry के लिए बहुत important है. Our old past example, we have discussed this example a lot of times before, and we're going to do the same over here. So equilibrium and ammonia production. Ammonia usually heavy process से carry out होता. This is nitrogen and hydrogen reacting to form ammonia. The equation is right in front of you, and it also tells you that the heat of reaction and enthalpy change for this reaction is negative 92 kilojoule per mole, which means it tells you that it is an exothermic reaction. Now, the Shirtlier principle tells us how to get the best yield out of ammonia for this specific reaction. High temperatures पर usually ऐसा होता है कि हमारे पास जब reaction faster होता है, position of equilibrium left पर चली जाती है क्योंकि reaction exothermic है. We already understand for exothermic reaction, अगर हम temperature बढ़ाते हैं, that doesn't go in the favor of the products, actually that goes in the favor of the reactants. So हम बड़े आराम से ये कह देते हैं कि आपके पास reaction जो है, ठीक है, उसमें position of equilibrium towards left shift कर रही है. Okay, so what happens if we increase the pressure? This is pretty much the same what we have been doing back in IGCSE. अगर आपको याद हो तो IGCSE में हम ये कहते थे कि 1 mole of this plus 3 moles of this is equal to total of 4 moles. And on the other hand, we have 2 moles. So since the number of moles of reactants is bigger and product is smaller, increasing the pressure would favor the product side. Now, the exact same thing happens, and increasing the pressure, what happens is that the equilibrium is shifted towards the right-hand side or towards the product side, and it increases the yield of ammonia. And the same thing is written over here. All right. Iman, it's not about your Wi-Fi's problem. I had an internet error day too. We weren't able to even start it at the right time, so I started approximately 15 minutes late. That's why we are just a few lines done. That's why we are hardly done with the first 4 or 5 lines. So no problem. I think you can catch up. Okay, so moving on. What happens if we decrease the temperature? Now, in that case, decrease in temperature decreases the energy of the surroundings. What happens is that the reaction goes in the direction where the energy would release. Since it's an exothermic reaction, the energy would be easily released if it goes into forward direction. So the position of equilibrium is shifted towards the right. The value of Kp also increases. Now, up to this point or this point is something we were done back in IGCSE. तो इसके लिए को बहुत ज़्यादा detail बताना या बहुत ज़्यादा difficulty level होना, I don't think you're gonna find any much of difficulty level over here, क्योंकि ये पहले भी किया हुआ है, ये वही Lee-Shirtlier principle है, ये वही disturbing factors हैं, और ये वही reattainment है for the dynamic equilibrium again. But what's important and what's new as per A level is something like this. Now this time you know that temperature affects the equilibrium constants or equilibrium constants in terms of concentration, in terms of pressure. आपको पता है कि Kc भी affect होता है temperature से, Kp भी affect होता है temperature से. ऐसी सूरत में Kp की value increase होगी, ठीक है? So जब भी हम कोई ऐसा काम कर रहे होंगे किसी भी reaction के लिए जिसमें product side favor होती है in terms of temperature, तो Kc या Kp की value actually increase कर रही होती है, ठीक है? बात समझ लें. This is very important. This is not written in straightforward words anywhere in the book, so we need to understand it. Temperature is the only factor that can affect Kc और Kp, right? ये हम पिछले 1-2 classes में ये बात कर चुके हैं. I hope you remember it. लेकिन जो बात समझने की है वो ये Kc या Kp की value increase तब होगी जब temperature के साथ कोई ऐसा काम किया जाएगा, कम करना या बढ़ाना, ऐसा जो रिएक्शन में प्रोडक्ट साइड को फेवर कर रहा होगा, पोजीशन ऑफ इक्विलिब्रियम को टुवर्ड्स राइट लेकर जा रहा होगा, तो Kc या Kp की वैल्यू इंक्रीज हो जाएगी. अगर वो लेफ्ट पर लेकर जा रहा होगा, ठीक है, या रिएक्टेंट साइड को फेवर कर रहा होगा, सो ऑफ कोर्स Kp या Kc की वैल्यू डिक्रीज हो जाएगी, ठीक है? तो एक्चुअली में क्या होता है, कि यहाँ पर Kc या Kp की वैल्यू हमारे पास डिक्रीज हो रही होती है, सॉरी ये प्रेशर था, माय बैड, हमें ऐसा नहीं कहना चाहिए, बल्कि Kc Kp वैल्यू इंक्रीज हो रही होती है जब हम टेम्परेचर को डिक्रीज करते हैं, और Kc या Kp की वैल्यू जो होती है वो डिक्रीज करती है जब हम टेम्परेचर को इंक्रीज कर रहे होते हैं. That is the specific case for ammonia. Ammonia by Haber's process, by the formation by the combination of nitrogen and hydrogen. ठीक है, तो रिमेंबर जब भी आप टेम्परेचर को ऐसे चेंज कर रहे होंगे कि वो प्रोडक्ट साइड फेवर कर रहा हो, Kc या Kp की वैल्यू इंक्रीज हो रही होगी, वाइस वर्सा डिक्रीज हो रही होगी. ठीक है, अपार्ट फ्रॉम प्रेशर एंड टेम्परेचर जो यहाँ पर डिस्कस किया हुआ है, अगर हम अमोनिया को रिमूव करें बाय कंडेंसिंग इट टू अ लिक्विड, रिमेंबर दिस सीम्स लाइक अ लाइन कि इससे हमारे पास किसी भी फैक्टर पर फर्क नहीं पड़ रहा होगा, बट इट इजंट एग्जैक्टली ट्रू. We had 4 factors to begin with. The factors that can disturb dynamic equilibrium, well, those factors were concentration, pressure, temperature, and catalyst. And this specific one is actually changing concentration of product or products, right? If you're taking out a product. Since it is a disturbing factor, as quoted over here, so yes, that brings a change. So whenever we're going to take out ammonia, which has a much higher boiling point than hydrogen and nitrogen, and I hope you remember it was minus 33 degrees centigrade back in the O-levels book, in which we specifically gave the value to the student. We never asked the student to cram the value, but just to joggle your memory, it was much lower than nitrogen or hydrogen. Since nitrogen was around minus 196 degrees centigrade or something, and hydrogen was around minus 252 degrees centigrade or something. Now, there is a huge difference, a gap between these values. So, position of equilibrium shifts towards the right to replace the ammonia that has been removed. The system tries to form more and more ammonia. So, by that, of course, the whole system is, or the equilibrium is shifted towards right, favors the product side, and more product is produced. Now, more ammonia formed from hydrogen and nitrogen actually tries to keep the value of Kp constant. Now, since you must be thinking that I have been talking about Kc/Kp all along, but let me tell you that was only for the concept. If I talk about this specific reaction, remember we are only going to consider Kp. Why? Because we consider Kc in all other states, but if the reaction is completely carried out in gaseous form, beat reactants and products at the same time, yeah, it is better to consider Kp instead of Kc. So for this one, just Kp. Right. So it changes from example to example, and as soon as you see the states of matter for reactants and products, it would give you a very easy idea of what do you need to consider. If it's all gases, Kp. If it's just a mixture of gases and most of the other states of matter are used, Kc. If under consideration stuff is gases and there are a couple of gases in there, you can use Kp. There is no problem in that. Okay. So moving on, equilibrium and production of sulfuric acid, contact process. We have done with this thing as well back in IGCSE, and you already know, as you can see in this reaction, this is also an exothermic reaction, a little bit more exothermic than what Haber's process was. So what happens when we increase the pressure? Again, this is a combination of 3 moles on reactant sides and 2 moles on product side. So of course, increasing the pressure is going to take it to the right hand side, and this would increase the yield of our product. Now, in practice, the reaction is carried out just above atmospheric pressure. This is because the value of Kp is very high. Now, when the value of Kp is very high, you need to understand the fact that the product formation is very much favored. Now, position of equilibrium is far over to the right, even at atmospheric pressure. Very high pressure is unnecessary and is not used since it is expensive. Now, this is going to give you an idea about the industry. And as you might have seen a habit of me that I always talk about industry in the terms of finance, finance, finance. So yeah, that is what industry is all about. Industry is all about making the product, selling those products, earning the profits. So yes, if not the very top priority, finance is one of their top priorities. So you need to think about industry in chemistry in such a way as if you are the greediest person on the planet. All right. So yeah, that is true. We think in terms of money. So think about it. The KP is already very high. The reaction is already favored towards the product side, and a product can be produced easily without giving it a lot of pressure. And high pressure takes some very sophisticated equipment, which is at the same time expensive. Why would industry waste money on this kind of expense when it can be done without increasing the atmospheric pressure? So if I joggle your memory and if we go back to O-level books, you might have seen, if we discuss the pressure for contact process alone, you might have seen that the books or the reference books usually quote the pressure around 1 to 2 atm atmospheric. Some of the books do quote 1 to 5 atm, but that's about it. They never quote anything higher than 5. Why? Industry does not even try to go for that kind of expense, because without even that expense, industry is going pretty profitable. So yeah, they think in terms of profit all the time. And that's what we are going to consider whenever we are talking about industrial chemistry. So moving on, what happens if we decrease the temperature? Decreasing the temperature shifts the position of equilibrium to the right. Of course, that's going to happen. It's an exothermic reaction. If we decrease the temperature, the reaction is going to work in such a way that it's going to go forward and it's going to favor the product side. This is exothermic reaction. Position of equilibrium favors SO3 production. Value of Kp increases. Now, what we do is that SO3 is removed by absorbing it in 98% sulfuric acid. This actually produces H2S2O7, which we have considered as pyrosulfuric acid. The other name was, there was another name, though I can't exactly remember the other name right now. There was another name to H2S2O7. I can't really remember it right now. So the SO3 reacts with the solution, eventually forming more H2SO4. How do we do it? And that was, yeah, oleum. Thank you for the tip. Yeah, that is oleum, and the oleum had a formula of H2S2O7, and reacting it with just pure water, mixing it with just pure water eventually produces double the amount of sulfuric acid. So that's why in a continuous process, SO3 is absorbed in H2SO4. This does not affect the equilibrium significantly, is because the position of equilibrium is already far over to the right. So yeah, we keep taking out the product all the time. Okay, so I guess this is pretty easy. Now, they have been very specific over here about most of the stuff. What they haven't been specific over here is that this discussion is much theoretical when it comes to temperature. I hope you understand they are talking about decreasing temperature and favoring the product side, which in O-level book is clearly written as uneconomical. Why? It takes too much time for the reaction to finish up. Instead, we do not decrease the temperature. This is theoretical discussion. In actual or in practical, what industry is doing is that industry is increasing its temperature to around 450 degrees centigrade for Haber's process, right? And this temperature actually favors the reaction as a whole. It does not make the reaction uneconomical. Though this does not favor the product side, this actually favors the reactant side. But imagine, our concentration steps giving reactants all the time we keep giving it reactants, we keep taking out the product, right? These are the two steps that we do all the time. And in case of pressure, we keep increasing the pressure. In case of catalyst, we use a very good catalyst. We use well-divided iron. Now, all these things in total can compensate the little bit of loss we are having over here. Otherwise, the reaction is so uneconomical, it takes more than 14 hours to complete. Now, if you think on your own, think about it a little. An industry which is taking more than 14 hours to complete the process, and then there is another industry and it is decreasing the temperature, it's going by the book, it's going theoretically. Then there is another industry which is actually going for a higher temperature with 450 degrees centigrade. Of course, higher temperature is going to require some fuel. We're going to burn some fuel, increase the temperature, but that temperature actually contributes a little bit towards kinetic energy. And for the rest, we compensate with the help of this. And that industry is capable of finishing it up in 6 to 8 hours, almost half of what we are giving over here. Do not quote these hours values anywhere in the paper. They will not be asked. I'm just telling you this because this is some advanced information. And with these pieces of information, it's actually easier for the student to understand the facts. So the word uneconomical is justified by this kind of explanation. So imagine the other industry, which is going for this kind of temperature, actually producing double the amount of ammonia in equal number of hours, 14 hours, will be going for double the profits. सोचे कि इंडस्ट्री 14 आवर्स में सिर्फ एक बैच कंप्लीट करती है, उसको सेल करती है, उसका प्रॉफिट अर्न करती है, और एक दूसरी इंडस्ट्री जो टेम्परेचर बढ़ा रही है, अगेंस्ट द बुक चल रही है, लेकिन उससे डबल अमाउंट में अमोनिया प्रोड्यूस कर रही है, डबल प्रॉफिट्स अर्न कर रही है. ऑफ कोर्स कौन ज्यादा बेहतर कर रहा है? It's not exactly anywhere that we should go by the book. Thinking out of the box, getting more profits has always been something that is attracted by most of the industrialists around the world. For the starters, it was a cliche, but now, yeah, it is the real deal. So moving on, if I talk about this process, contact process, again, I hope you understand that book says the same thing. We do not decrease the temperature. We almost use the same value of around 450 degrees centigrade temperature, around, not exactly, around 450 degrees centigrade temperature. Again, the industry is not uneconomical anymore, and we have many other ways to compensate the reversal that is going to happen because of high temperature. I hope I make my point clear. Let's move further. This was the only part about industry. Next up is something different. We discuss acid and base equilibria. Now, acid and base equilibria is about neutralization reactions, and specifically the ones which do not consider strong acid or strong alkali. Instead, consider the weak acid or alkali conditions. Let's talk about that. Starting off with pH values and neutralization, we do understand that universal indicator, pH meter, can deduce easily whether a substance is acidic, alkaline, or neutral. You understand the pH level. Anything having pH below 7 is acidic, above 7 is alkaline, and neutral has exactly a pH of 7. Neutralization itself is a process in which acid and alkali, actually parts of them H positive from acid mostly and OH negative from alkali or from the base, react one another, neutralize one another, and the reaction produces water along with the salt. Though the salt ions have been spectator ions, but we have been calling them all along, and that's right, but the purpose of this whole reaction is to produce water, a neutral species. Now, I hope you understand the simple generic equation. Acid plus alkali gives us salt plus water, sodium sulfate and barium chloride are salts over here. The simplest ionic equation for neutralization reaction every time comes out to be H positive, OH negative, giving us water. दुनिया का जो मर्जी न्यूट्रलाइजेशन रिएक्शन उसकी आने की इक्वेशन यही बनती है. एक सिंपल टिप होती है जो हम ओ लेवल्स में बच्चों को बता देते हैं, पता होता है कि अगर वो न्यूट्रलाइजेशन रिएक्शन है, कोई जरूरत नहीं है सारे आयंस काटने की, स्पेक्टेटर्स निकालने की. No, it's going to turn up like this. If it's a pure acid alkali equation, I'm not talking about acid bases, this can be something very different. Okay. So simple definition, acids और bases की, acid को हम define कर देते हैं एक ऐसा substance जो neutralize कर सकता है, base को salt और water form कर सकता है, ठीक है. तो एक बड़ा अच्छा तरीका acid को define करने का. Remember हमने acid के से ज़्यादा अच्छे तरीके से या और भी definitions पहले से कर रखी हैं, ठीक. हम उसकी तरफ भी आते हैं. सो सिंपल डेफिनेशन बेस की होगी, ऐसा सब्सटेंस एसिड को न्यूट्रलाइज कर देता है। वेल बेस होता क्या है? एक ऐसा कंपाउंड जिसके अंदर ऑक्साइड या हाइड्रोक्साइड आयंस होते हैं, दे रिएक्ट विद एसिड्स, दे फॉर्म सॉल्ट एंड वाटर। अल्कलीज वो बेसेस होती हैं जो सॉल्युबल इन वाटर होती हैं, राइट? अल्कलीज और बेसिस का डिफरेंस यूजुअली हम वेन्स डायग्राम से बताते हैं, एंड आई होप यू रिमेंबर कि बेसिक बिगर ब्रॉडर वर्ड है और उसमें एक छोटा पार्ट होता है जिसे हम alkali कहते हैं. Venn diagrams are usually circle inside circles, and these nested circles can easily explain the bigger broader term or the smaller term. Base in this case is the bigger broader term, alkali is the smaller term. Now, moving further, अगर हम कुछ acids के formula table 8.8 में देखें, we're going to see that they all contain hydrogen atoms. Acids को water में dissolve करें, ये ionize होते हैं, hydrogen ions form करते हैं, and then the anions, whatever the possible anions are with them. नोट करें कि ऑर्गेनिक एसिड्स जैसे कि कार्बोक्सिलिक एसिड्स हैं, उसमें से सिर्फ कुछ हाइड्रोजन एटम्स केपेबल होते हैं कि वो आयंस बनाएं, सब हाइड्रोजन एटम्स एसिडिक नहीं होते. दिस इज समथिंग दैट वी आर this is what Venn diagram usually tells us, Iman. All alkalis are bases, but not all bases are alkalis, because all of the bases in the word are not soluble. Only some are soluble, hence the term alkali. Okay, and yes, that is right. So moving on, आपको एक सिंपल डायग्राम विनेगर बेकिंग सोडा की दी हुई है और हमारे पास उसके रिएक्शन के लिए बताया हुआ है, ठीक है. अपार्ट फ्रॉम दैट, एसिड बेस इक्विलिब्रिया ह्यूमन बॉडी में बहुत इंपॉर्टेंट होता है. हमारे पास अब ये वो 8.8 टेबल आया है. इफ यू लुक एट दिस टेबल, ही वाज टॉकिंग अबाउट समथिंग स्पेसिफिक जो मोल लेवल में भी बता चुके होते हैं कि आपके पास ऑलमोस्ट एवरी एसिड consists of hydrogen ions, but you're going to notice there are some organic acids in which the hydrogen ions that are given out as acids are some specific ones. There are some other hydrogen ions present or atoms present in the system, but they are not considered as ionizable ions or acidic hydrogen. Remember, इस हाइड्रोजन के लिए हम वर्ड यूज करेंगे either ionizable hydrogen, राइट? आयनाइजेबल हाइड्रोजन ऐसा हाइड्रोजन होता है जो आयंस की फॉर्म में सेपरेट आउट हो जाता है. हम इसके लिए एक और टर्म भी यूज करते हैं, एसिडिक हाइड्रोजन आयंस, राइट? Because they later on get detached from the whole thing by forming separate H positive ions in water. So yeah, acidic hydrogen. I hope you get the point. Do you? Okay. All right. Moving on. Now, you must know the names and formulae of first 4 acids in table 8.8. अगर आपको बेंजोइक एसिड का नहीं पता, that's fine. हम बेंजीन बेस एसिड्स इतनी डिटेल में नहीं बताते, लेकिन फर्स्ट 4 एसिड इतने फेमिलियर होते हैं हम ओ लेवल से कि उसके नेम्स में, फॉर्मूलाए में, या इवन इन इक्वेशंस में आपको कोई प्रॉब्लम नहीं होता है, ठीक है. सो बेटर डेफिनेशन, एसिड की ऐसा सब्सटेंस हो जाएगा जो रिलीज करे हाइड्रोजन आयंस जब हम उससे डिसॉल्व करें वाटर में. Now, here comes a little bit of theoretical parts. A level की बुक यहाँ पर आपको different scientists की theories पढ़ा रही है. Let me be honest. बहुत सारे साइंटिस्ट पास में हिस्ट्री में ऐसे आए जिनने अपने अपने अंदाज में एसिड को डिफाइन किया, ठीक है. आपको याद होगा कि हमने एसिड को डिफाइन किया था एक ऐसी चीज जिसकी pH below 7 है, ठीक है, सॉरी below 7 है. हमने ऐसे भी एसिड को डिफाइन किया. हमने ऐसे भी एसिड को डिफाइन किया कि वो H पॉजिटिव आयंस का एक्सेस देता है जब हम उसे वाटर में डिसॉल्व करते हैं. हमने ऐसे भी एसिड को डिफाइन किया है कि वो H पॉजिटिव का डोनर होता है जब वो रिएक्ट करता है किसी रिएक्शन में. तो वो सब डेफिनेशंस 1 by 1 आ रही हैं. इसी के बीच में हमने एक डेफिनेशन ऐसी की थी कि एसिड जो होता है वो कोई भी ऐसी स्पीसी है जो न्यूट्रलाइज कर सकता है बेस को और प्रोड्यूस कर सकता है सॉल्ट या वाटर. बेसिकली वाटर लिखना इंपॉर्टेंट है क्योंकि वो प्रोडक्शन है न्यूट्रलाइजेशन एसिड की. सॉल्ट तो जो स्पेक्टेटेड आयंस है, कोलैटरल प्रोडक्ट है, ठीक है. तो हाँ बिल्कुल, लिटमस पेपर या पीएच जो है वो एक ही मानों में आता है, लिहाजा लिटमस वाली डेफिनेशन स्लोली पुरानी हो गई और हमने उसे पीएच के स्केल से रिप्लेस कर दिया. इसलिए लिटमस की सेपरेट डेफिनेशन अब हम नहीं बताते। Although yeah, if we go way back, हाँ बिल्कुल, लिटमस एक साइंटिस्ट के रेफरेंस से है और एक बड़े अरसे तक लिटमस की डेफिनेशन एसिड के लिए चलती रही है। You're right about that. लेकिन अब की अगर आप ओ लेवल की बुक्स उठाएंगे तो लिटमस पेपर एक स्पेशल डेफिनेशन के तौर पे कैटर नहीं होता। So one of these is this, one of these is this, one of these this, and one of these this. ठीक है, तो ये डिफरेंट साइंटिस्ट की थ्योरीज हैं अबाउट व्हाट एसिड्स आर और हाउ वी कैन डिफाइन देम। आपकी बुक क्या कर रही है कि वन बाय वन इन सारों को डिस्कस करती चली जा रही है। अगर आप कोई भी और कन्वेंशनल बुक देखेंगे तो वहां क्या होता है कि वहां इस डेफिनेशन के साथ हमने यूजुअली साइंटिस्ट का नेम दिया होता है कि इस साइंटिस्ट ने ये डेफिनेशन दी, इस साइंटिस्ट ने ये डेफिनेशन दी। तो आपको ये किसी भी और बुक में, लेट्स सपोज ये वाली डेफिनेशन जो अभी आपके सामने दी हुई है, ठीक है, ये डेफिनेशन आपको मिलेगी आर्हेनियस कॉन्सेप्ट के तौर पे। Arrhenius was the name of a scientist. He has done too much in chemistry and even in other fields of science. So Arrhenius concept के तौर पे ये आपको आगे चलकर लोरी ब्रॉन्स्टेड कॉन्सेप्ट के तौर पे मिलेगा। ठीक है, ब्रॉन्स्टेड लोरी भी लिखते हैं, टू डिफरेंट साइंटिस्ट, जिसका मर्जी नाम पहले बाद में लिखते हैं, ब्रिटिश एंड अमेरिकन सिस्टम, या कीप चेंजिंग ऑन द फर्स्ट नेम। ठीक है, तो आपको डिफरेंट साइंटिस्ट के नेम्स के साथ मिलेंगे। सो वेदर यू फाइंड द नेम्स ओवर देयर और नॉट, there is one thing that I keep saying all the time कि history, years या names of scientists कभी भी O या A level में टेस्ट नहीं किए जाते। It's not about your knowledge of history that they actually target. So that is something important, but that's a discussion for some other time, some other day. Okay, so this is another definition. अगर आप इस equation को देखें तो ये prove भी करती है कि हाइड्रोजन आयंस देते हैं जो whenever they are dissolved in water and actually they give an excess of hydrogen ions. Now many metal oxides और hydroxide bases होती हैं, उन bases को जब हम water में dissolve करते हैं तो वो hydroxide ion solution में देते हैं। वो base जो water soluble होती है उसे हम alkali कहते हैं। So an alkali is something like this, ठीक है। लेकिन कुछ ऐसी चीजें भी होती हैं जिनके अंदर खुद OH नेगेटिव नहीं होता, लेकिन जब उन्हें वाटर के अंदर डिसॉल्व किया जाए तो लिटरली वाटर से रिएक्ट करके OH नेगेटिव प्रोड्यूस कर देते हैं। अमोनिया वाज अ बिग एग्जांपल आउट ऑफ दिस। ठीक है, सो हम एक्वस अमोनिया को अल्कली कहना शुरू कर देते हैं। ठीक है, आप नोटिस कर दीजिए होगा कि अमोनिया को अल्कली नहीं कहा जाता, अमोनिया सोल्यूशन को या एक्वस अमोनिया को अल्कली कहा जाता है। ठीक है, अमोनिया जब तक गैसियस फॉर्म में होती है तो हम इसे अल्कली नहीं अल्कलाइन गैस कहते हैं। So make sure that you're using the right terms about it based upon the state symbol given next to it. अगर NH3 आपके पास दिया हुआ है gaseous form में तो it's an alkaline gas. अगर NH3 आपके पास aqueous form में दिया हुआ है, it's ammonia solution or aqueous ammonia, which is definitely an alkali. To be honest, इसके लिए हम ये एक separate formula भी show कर सकते हैं। ठीक है, ऐसे भी शो कर सकते हैं, लेकिन हम यूं भी शो कर देते हैं और हम यूं भी शो कर देते हैं। देयर इज नो डिफरेंस। आप दोनों तरीके से पेपर्स में ऐसा हुआ देखा करेंगे। ठीक है, और हम जानते हैं NH4 पॉजिटिव अमोनियम आयन है और अमोनियम आयन वाटर से हाइड्रोजन आयन लेकर एक्सेप्ट करके बनता है। सो हमने बेस की एक वाइडर डेफिनेशन स्टार्ट कर दी कि वो जो हाइड्रोजन आयंस को एक्सेप्ट करे। ये वही कॉन्सेप्ट है जिसको मैं अभी लोरी ब्रॉन्स्टेड कॉन्सेप्ट का नाम दे रहा था, जिसमें एसिड्स को हम क्या डिफाइन करते हैं कि वो H पॉजिटिव के डोनर्स हैं और हम बेसिस को डिफाइन करना शुरू कर देते हैं H पॉजिटिव के एक्सेप्टर्स के तौर पे। हम उसे OH नेगेटिव के हिसाब से नहीं डिफाइन करते, हम उसे H पॉजिटिव का एक्सेप्टर कहना शुरू कर देते हैं। अमोनियम आयन की फॉर्मेशन या अमोनिया के लिए बेस का वर्ड यूज करना वो बेसिकली इन डेफिनेशंस में आ रहा होता है। तो ये एक और कॉन्सेप्ट, एक और थ्योरी है जो इसको एक्सप्लेन करती है। सो कॉमन अल्कलीज में हमारे पास सोडियम हाइड्रोक्साइड, पोटेशियम हाइड्रोक्साइड और अमोनिया सॉल्यूशन आता है, एक्वस अमोनिया। ठीक है, सो मूविंग ऑन, उसके अलावा हमारे पास कैल्शियम ऑक्साइड, कॉपर ऑक्साइड भी एग्जिस्ट करते हैं, कैल्शियम हाइड्रोक्साइड भी है। ठीक, तो उसमें काफी सारे यहाँ पे बेसिस के नाम दिए हुए हैं। ठीक, लोरी ब्रॉन्स्टेड कॉन्सेप्ट को फर्दर डिस्कस करने की जरूरत है बिकॉज इट्स नॉट जस्ट प्रोटॉन डोनर एंड प्रोटॉन रिसेप्टर दैट वी नीड टू डिस्कस, देयर इज मच मोर टू दिस थ्योरी which is a part of A-level syllabus. So specifically let's discuss that. Definition acids और bases की earlier times में limited हैं reactions में जो water के अंदर होते थे, 1923 में एक डैनिश केमिस्ट ने, जे ब्रॉन्स्टेड ने, और एक इंग्लिश केमिस्ट ने, टी लॉरी ने सजेस्ट की मोर जनरल डेफिनेशन। ठीक है, ये डेफिनेशन इस आइडिया पे बेस्ड थी कि एसिड बेस्ड रिएक्शन में प्रोटॉन ट्रांसफर होता है। ये ट्रांसफर एसिड से बेस पर हो रहा होता है, तो हम एसिड को प्रोटॉन डोनर और बेस को सिंपली एक्सेप्टर बुला देते हैं। और ये बहुत सारे रिएक्शंस में पॉसिबल है। फॉर एग्जांपल, हाइड्रोक्लोरिक एसिड को जब हम वाटर में डिसॉल्व करते हैं, एक्चुअली ये फॉर्म तब होता है जब हाइड्रोजन क्लोराइड गैस डिसॉल्व की जाती है वाटर में, और फिर आपके पास हाइड्रोक्लोरिक एसिड का सॉल्यूशन बनता है। टू बी ऑनेस्ट, हाइड्रोक्लोरिक एसिड के अंदर हाइड्रोक्सिनियम आयंस होते हैं, ठीक है, H3O पॉजिटिव, और क्लोराइड आयंस होते हैं। अब इन आयंस की फॉर्मेशन भी हम जानते हैं कि अगर H2O के अंदर एक हाइड्रोजन आयन और एक्सेप्ट हो डेटिव बॉन्डिंग से, ऑक्सीजन बाकायदा अपना लोड पे डोनेट करता है, इसलिए दो H3O पॉजिटिव या हाइड्रोक्सिनियम आयंस फॉर्म होते हैं। ठीक है, so the formation of these ions is actually the very good way of defining this whole concept. हाइड्रोक्लोरिक एसिड एक एसिड हो गया क्योंकि ये H पॉजिटिव आयंस डोनेट कर रहा है या प्रोटॉन डोनेट कर रहा है वाटर को, और वाटर इस केस में लोरी ब्रॉन्स्टेड बेस हो जाएगा क्योंकि वो प्रोटॉन एक्सेप्ट कर रहा है। ठीक है, सो इस कॉन्सेप्ट के बाद हमने बेसिस को या एसिड्स को लोरी ब्रॉन्स्टेड एसिड्स या लोरी ब्रॉन्स्टेड बेसिस के तरीके से बताना शुरू कर दिया। Now, anything can be considered as a Loring Bronsted acid as far as it is a proton donor, and anything can be accepted as a Loring Bronsted base as far as it is a proton acceptor. It does not actually matter कि उसकी pH क्या है। ठीक है, तो इसमें ये वाली डिस्कशन जो pH रिलेटेड थी वो नहीं थी, ये एक बहुत जनरल डेफिनेशन थी, और ये डेफिनेशन बहुत सारे ऐसे एसिड्स और बेसिस जिनके ऊपर उस वक्त में क्वेश्चन मार्क लग चुका हुआ था उसको डिफाइन करने के काबिल थी। So yeah, it was widely accepted for this reason. Okay, so moving on, there are other cases which we definitely need to study. उसने बाकायदा HCl का वाटर के अंदर प्रोटॉन डोनेशन, उसके अंदर जो कोवलेंट कोऑर्डिनेट कोवलेंट बॉन्ड या डेटिव बॉन्ड से हाइड्रोक्सिनियम आयंस की फॉर्मेशन है, उसको डिस्कस की। और नॉट जस्ट दैट, अगर आप अमोनियम आयन की बात करें तो वो भी डेटिव बॉन्डिंग से फॉर्म होता है। डेटिव बॉन्डिंग पता कैसे चलती है? जैसे ही आप किसी स्ट्रक्चर को देखेंगे, अगर शेयर्ड पेयर डॉट क्रॉस से बना हुआ है वो कोवलेंट है, डॉट क्रॉस से बना हुआ कोवलेंट है, अगर वो डॉट डॉट से या क्रॉस क्रॉस से बना हुआ है वो डेटिव है। That's a very easy way to see it. As soon as you see a diagram and you see the shared parts, you can literally identify every shared pair, whether it's covalent or it's dative, by this simple idea. Dot cross, covalent, either it's a dot dot or cross cross, similar signs, it's dative. ठीक है, so वो यहाँ पर clearly हमें पता चल जाता है। Moving on, अगर यही चीज हम डिस्कस करें for ammonium ions, so of course ये भी possible है। Now this is a very different reaction. Take a look. Water is reacting with ammonia and forming ammonium ion and hydroxide ions, but in this case water is considered as an acid because it donates the proton, and on the other hand ammonia is considered the base because it accepts the proton. Now you must be thinking that water is behaving in two different ways. It's an acid in this reaction and it's a base in this one. Yes, that is true. Water इस reaction में base है और water इस reaction में acid है। So जब ऐसा होगा, substances जो कि water की तरह होते हैं, ये different reactions में different behave करते हैं. In some reactions acids, in some reactions bases, we call them amphoteric. Amphoteric means having dual behavior. I hope you remember this word specifically from O levels when we were bifurcating oxides and we used the term amphoteric oxides or amphoteric hydroxides. Those were the ones which were capable of showing the acidic behavior and the basic behavior at the same time. There were some acidic oxide capable of only showing acidic behavior. There were some basic oxides capable of only showing basic behavior. Amphoteric were the ones that were simultaneously capable of showing both behaviors, and neutral were the ones which were capable of showing neither kind of behavior, neither acidic nor alkaline, nor basic. And yes, zinc oxide, aluminum oxide, beryllium oxide, these three very specific examples from O levels were given as the examples of oxides, these oxides. But here, the amphoteric means something differently. We're not talking about oxides originally, but we are talking about in the similar meaning that it may act as an acid or it may act as a base. Now, Lowry-Bronsted acids and bases do not have to involve aqueous solutions, and that is something which actually made Lowry-Bronsted concept much more famous than the previous ones. For example, when chloric 7 acid, HClO4, we also call it perchloric acid. Now, when this reacts with ethanoic acid, CH3COOH, in an inert solvent, not water, non-aqueous we're talking about, the following equilibrium is set up. In this specific equilibrium, of course, we are now comparing one more acidic acid with one less acidic, or you can say one stronger acid with a weaker acid. Now, I do understand that we call anything acid if it produces H positive ions in water. Without water, an acid is not an acid. But the best part about Lowry-Bronsted concept was it can even work for non-aqueous inert solvents. And even in those solvents, if the whole system can be based and one of them can donate a hydrogen to the other one, of course, the one that is proton donor would be considered an acid and the acceptor as a base. Well, I forgot to joggle one piece of memory. H positive is known as a proton because hydrogen is made up of just one electron and a proton, since there is no neutron. And when it loses the electron, it becomes proton. So there is only a proton in this structure. That's why we keep calling it proton. So since HClO4, chloric 7 acid in this case, is donating a proton to CH3COOH in an inert solvent, they becomes respectively the acid and the base. Now, so this gave a huge fame to this theory because this theory was capable of telling or differentiating between acids and bases with the kind of definition that never even required water to prove itself. Now, when an acid or base reacts with water, an equilibrium mixture is formed. For acids such as hydrochloric acid, the position of equilibrium is almost entirely in the favor of products. But for ammonia, which is not a very strong acid, believe me, the position of equilibrium favors the reactants. The equations can be written to show this. We can show it like this, we can show it like this, right? Now, as you can see, they have used aqueous, the word water, and this arrow shows that it is almost an irreversible reaction. All of the acid has been converted into positive and negative ions, which means the reaction has almost already gone to completion. However, a reversible arrow shows over here that the reaction will never go to completion. Never, not just does not, it would never go to completion, and the products can always break down to give us reactants, and hence an equilibrium arrow. And this equilibrium arrow definitely should give you the concept that it can establish as a dynamic equilibrium. Now, for dynamic equilibrium, Le Chatelier principle can be considered true, which means any equation like this for an acid or a base can be given an exam, and Le Chatelier principle with different of its disturbing factors that can disturb and retain the dynamic equilibrium can be discussed. For example, if you want this reaction to move further towards the right or favor product side, you can always add water to it. Or if you add some alkali in this reaction which produces more OH negative ions, the system would try to go back and favor the reactant side. So yeah, any external factor or change will be applied to this reaction like any other dynamic equilibria, and Le Chatelier principle will be considered to get our answers theoretically. I hope that explains it. Okay, so moving on, we do understand the difference between strong acids and strong bases, or the weak ones. Okay, this might take more time than what we have originally. For the class today,